this idea of using biological information to try to find drug candidates is something that I guess 10 years ago I was thinking about a fair bit. So do you have any like interesting case studies? I mean, obviously you can't go into proprietary things that you're doing at Exscientia, but yeah.
Yeah, so I should say, obviously I have two jobs still. So yes. I'm CSO at Exscientia, but I'm also a professor in the Department of Statistics at Oxford.
Yep.
And so I can talk some about our work there, but they're obviously related. So the easiest recent example to talk about is when you mentioned that concept of protein structure prediction. Everybody has heard of AlphaFold. It made quite a lot of noise about being able to predict protein structures. Mm-hmm. We've done a lot of work on if you want to predict the structures of antibodies, you might want a model which is, instead of being general for all proteins, you make the model specialist for antibodies. Mm. And the reasons you want to do that, I mean, there's sort of the obvious reason, of course, if you can specialize a model, you might be able to make it more accurate. But it's also about the types of data you have available to you. So you can change the way we structure the model. Some of the things that become important in this are things like we don't use some of the functions that are used in AlphaFold, so we can go much faster. So it's much, much more rapid. But the sort of interesting internal machine learning parts of this are thinking about how you use the loss function, because the majority of the antibody is always the same shape. So if you use a standard loss function, you might not actually collapse to the correct structure because you just get most of it right. And that's fine if you're AlphaFold because, you know, you're mostly getting most proteins right. Whereas I'm really interested in the bits which we're getting wrong currently, because the rest of it I could have predicted anyway, because they're all the same shape. And the bit which is different is where the binding happens. So you want to refocus the way you use these types of functions to do that kind of thing. So it's a kind of that kind of work. So this is a paper we've put out recently, if people look at it, called Immune Builder, but it's using those kinds of ideas about how you take the data in, how you use your loss functions, and it's actually changes the kinds of results you can get or how you focus your kind of computational work.
So do you kind of start from scratch if you know some of the structure? Does that mean that you can kind of have, this is like, I'm probably mixing terminologies here, but in Bayesian statistics, we have like priors. And so do you kind of have like that kind of prior information that you can provide to the model?
So this is actually interesting. And when we built our first versions of this, we built something which is called AbLooper. And effectively, we did provide it with, here is the right answer for the majority of the structure. And I just want you to predict what are called these complementary determining regions, this difficult bit to predict. And that is really fast, actually. That's the fastest kind of prediction software we've written. We then went on to test, well, what if we let the model predict the whole thing? Because it will find it easy to predict the main part, and we play with these ideas about loss functions. And that's where we moved on to Immune Builder. And I still don't completely understand why. We have some theories of why, but the second version is more accurate.
Right.
Even though we're asking it, in inverted commas, a harder question.
Right.
Now, it might be because it has better control of the overall function, because it's not set up like a prior here. You actually just literally provide it with the information of what this piece is, and then it has to fit onto that. And that's possibly why this happens.
Right.
But it turns out, even though it's sort of an easy question to answer and it slows us down in terms of making predictions, you make a bit better predictions if you do the whole thing as one concerted prediction inside these types of methods.
Nice. So then is there an easy way to explain without having to have a whiteboard or other kinds of visuals for our audio-only listeners? Is there a way to kind of intuitively explain how we can set up a loss function to handle this situation that you're describing, where we know some of the structure and we want to give clues to that part?
So it's almost like not giving clues to that part. It is changing the weighting of the loss function. So in some sense, you know you're going to get that bit right. So if you imagine, this is explaining it very poorly, I'm afraid, but if you imagine that if you had a loss function that said, how good is my overall structure, then it kind of drops straight down very quickly because the overall structure is really good. Yeah. And then most of the changes it makes as it's trying to learn don't affect improving the CDRs. So the loss function doesn't move. So the bet that was predicted badly doesn't improve as much as you want it to. Whereas if you reweight the loss function, so the set of atoms that you know you're going to get right, you actually don't give it much reward for doing so. Because even if you did barely train for that, it sounds awful, it will get them right anyway.
Right.
So it's basically balancing out the parts. Another part of the loss function we found, which was good to be able to do, was this idea of actually you could make the loss function less strict. And there are various reasons behind this compared to the way AlphaFold was trained. Some of it is because however strict you make the loss function in terms of trying to make the ideal structure, you never actually make something that's physically completely accurate. So you always have to do a bit of physics on the end. You do a sort of bit of minimization to make all the bonds and angles. So you can waste, it sounds weird, waste less time trying to make it get really great bonds and angles because you know you're going to run this kind of minimization on the end. So you have a loss function that's sort of slightly different there as well.